Hey everyone, so we're going to revise the idea of metal reactivity series in today's video, and we're going to see what are the basic connotations of the reactivity series. So we know it starts from potassium, sodium, lithium, then it goes on till lead, then we have hydrogen for comparison, and then we have copper and silver. We know the metals which are higher in the series, they react with cold water without any need for heat. And when they react with cold water, they release hydrogen gas to make their alkalis. So hydrogen was one of the byproducts, and they make alkalis like potassium hydroxide, sodium hydroxide. The metals from magnesium till silver, they don't react with cold water and they do not make their alkalis. They only react with steam. They make metal oxides in that case, not hydroxides, metal oxides. So they react with steam to make metal oxide plus hydrogen gas. We also saw in the last video that from potassium till lead, which are above hydrogen, these metals are considered above hydrogen in the series, so they did react with dilute acids. They react with dilute acids, where we even watched how on a microscopic scale it works. They make their salts depending on the acid, and they release hydrogen gas because the metal was donating its electron to the hydrogen ion of the acid. However, the metals which are below hydrogen like copper and silver, they do not give their electrons to hydrogen ions. So they don't technically react with dilute acids. They don't make their salts that easily, and then they don't release hydrogen gas as well. They only react with concentrated acids, but that's not a part of our syllabus, so we can skip that. We know the metals which are above hydrogen in the series can displace hydrogen, and the metals which are below hydrogen in the series can't displace hydrogen. And that's the basic idea of the series. So we know that there are few metals which are more reactive, like from potassium, sodium, lithium. The ones which are higher in the series are very reactive. They easily lose their electrons, they become cations, and they make really stable ionic lattices. So they make stable compounds like stable metal carbonates, stable metal nitrates, stable metal hydroxides. And these compounds have really stable ionic lattice. So carbonates, nitrates, hydroxides. But if you talk about metals which are below in the reactivity series, they are very less reactive. So they don't lose their electrons that easily. And when they don't lose their electrons that easily, they don't make good cations. They don't want to make ionic lattice. Their compounds can't be made. And even if you get their compounds, they won't be stable, so they will decompose. Their compounds are unstable. For example, the carbonates of copper, silver, the nitrates of these metals, they are not stable, they decompose really quickly. And then you get pure metal or perhaps any other substance really easily. The metals which are in the middle, so their reactivity varies. For example, calcium compound would be more stable than iron compound because that's a comparative reason over here. Now let's imagine we're going to study the stability of metal carbonates. So I have over here the entire series, and I'm writing the chemical formula for carbonates like potassium carbonate, sodium, lithium, calcium carbonate, aluminium carbonate, and all the way till below. For example, zinc carbonate, then iron, lead, copper, silver. So when we talk about the stability, potassium, sodium, and lithium carbonate are really stable. When you heat them, they won't decompose. They won't change their identities, they won't react, they won't release any gas over here. So they are stable, they are not going to decompose that easily. But when we talk about the other metal carbonates, the ones starting from calcium carbonate and then till below the series, they are unstable. So when calcium carbonate is heated, you get calcium oxide and carbon dioxide escapes. Magnesium carbonate is heated to give you magnesium oxide, and then again carbon dioxide escapes. Similarly, aluminium oxide can be the product in case of aluminium carbonate, and then again carbon dioxide is released. It goes on till copper oxide and carbon dioxide escaping. Silver carbonate is so unstable that you don't even get silver oxide. Silver is so unreactive that it wants to stay alone. So you will get pure silver and then oxygen and carbon dioxide is released. I'm balancing this equation, but the main idea is that silver oxide can't be even made, it's pure silver. Imagine you have 4 test tubes and each test tube was then placed onto a mass balance over here. Imagine you have the same amount of 4 different metal carbonates over here. So it's like 2.00 grams of 4 different metal carbonates. You have a mass balance to measure these values. So I'm going to keep the same mass balance for all these test tubes for fair result obviously. I have 2.00 grams of 4 different metal carbonates. Let's identify them as sodium carbonate, calcium carbonate, iron carbonate and copper carbonate. Now if I remove the mass balance and if I start heating these 4 substances, I want to make sure that all the other factors are equally fair. So I'm gonna heat them for the same length of time, for example 1 minute or 2 minutes or 5 minutes, whatever length of time, but it will be same for all these samples, and the same flame length, or you can say the height of the flame should be same, because you don't want other factors to meddle. Only the identities are different. You will observe that calcium carbonate releases a gas, iron carbonate and even copper carbonate release a gas, but sodium carbonate won't show a single change. This gas is none other than carbon dioxide. So when carbon dioxide escapes, the mass of test tube decreases. It becomes 1.12 in the case of calcium carbonate. In the case of iron carbonate, it becomes 1.24 grams, and in the case of copper carbonate, it becomes 1.29 grams. What happened to the mass decreasing? It's because carbon dioxide gas was escaping for all the other carbonates, while sodium carbonate remained the same. For example, in case of calcium carbonate, it is 0.88 gram escaping, and the remaining 1.12 gram is calcium oxide. In the case of iron carbonate, you can see that almost 0.76 gram escaped as carbon dioxide, and the remaining mass was iron oxide. In the case of copper carbonate, 0.71 gram carbon dioxide escaped, and the remaining mass was copper oxide. Sodium carbonate, on the other hand, did not change at all, because sodium carbonate was very stable. So since sodium is higher in the reactivity series, it did not decompose. You did not receive any carbon dioxide gas coming out of the test tube. Calcium carbonate decomposition was slower, iron carbonate was faster, and copper carbonate's decomposition was the fastest. To compare this, we're going to have the same test tubes, but this time we are going to have a gas syringe with a delivery tube on all 4 test tubes. I'm gonna measure the time required for the decomposition. So for that, I have 4 stopwatches. Now, if I start heating them, I'm going to receive carbon dioxide gas from all the test tubes if the reaction happens. Like in the case of sodium carbonate, there won't be any decomposition. But calcium carbonate took 25 minutes to decompose, iron carbonate took only 14 minutes, and copper carbonate only took 4 minutes to release the same amount of carbon dioxide gas. Why is that the case? Because copper carbonate was so unstable that it only took 4 minutes to decompose, but calcium carbonate was higher in the series, so it was a little less stable and it took more time. So the time required also depends on the position of the metal. If a metal is higher in the series, its compounds are stable. If a metal is lower in the series, its compounds are unstable and will decompose really quickly. I hope you guys will remember that. Stay tuned for the next video, guys. Thanks.